Hello, friend. Come close. Settle in. Tonight we're going somewhere quiet, somewhere most people never think to look. Some nights the world feels wider than it should. Stars breathe slower. Time folds in silence. Maybe that's just the mind listening to itself. Or maybe it's listening to something deeper. We walk through our days believing in smoothness, the floor beneath our feet, the air against our skin, the steady, unbroken flow of seconds into minutes, into hours. We trust that space is continuous, that between here and there are infinite points, infinite places we could pause, if only we move slowly enough. We believe time is a river, but what if it isn't? What if the universe beneath everything, beneath atoms, beneath the very stage where existence performs, what if it crumbles? What if space and time, those two things we've never questioned, are not smooth at all? What if reality pixelates? Before we drift into that question, I want to thank you for being here. If you find comfort in these quiet journeys through science and wonder, you might like to stay a while. You can gently tap the like button. It helps more than you'd think. Subscribe if you'd like more stories told softly. And ring the little bell, not for noise, but so the next quiet night can find you again when you need it most. Now, let's drift. Tonight we'll descend beneath the fabric of everything. We'll walk with the scientists who dared to ask if space itself might end, if time itself might tick instead of flow. We'll visit the smallest scales imaginable, places where the rules we know dissolve into something stranger, something that shimmers at the edge of mathematics and dream. You don't need to understand it all, just rest. Let curiosity do the listening. We live our lives on surfaces we trust: wood and stone, skin and silk, water so still it mirrors the sky. These things feel solid, continuous, real. We've built entire civilizations on the assumption that the universe is smooth, that you can always zoom in a little closer, divide a little further, measure a little more precisely. For thousands of years, we believed this without question. The ancient Greeks wrestled with infinity. Zeno of Elea, around 450 BCE, proposed his famous paradoxes puzzles designed to break the brain. To walk across a room, he said you must first walk halfway, then half of the remaining distance, then half again, infinitely. You'd have to complete an infinite number of steps, which should take forever. And yet somehow, we cross rooms every day. Zeno wasn't trying to prove motion was impossible. He was showing us something deeper, that infinity hides in the smallest spaces, that between any 2 points there might be everything. His paradoxes haunted mathematics for centuries. They whispered a question no one wanted to answer. Is space truly divisible forever? Or does it end somewhere at some final, unsplittable grain? Most chose to believe in continuity. It felt right. It felt true. Isaac Newton in 1687 gave us a universe built on absolute space and time. Space, he said, was a vast unchanging stage, smooth, infinite, perfectly still. Time flowed at the same rate everywhere, for everyone, forever. Seconds ticked uniformly across the cosmos. An hour on Earth was an hour on Jupiter, an hour in the farthest star. It was a comforting vision. The universe is a great clock, its gears turning smoothly, predictably, eternally. And for 200 years, it worked beautifully. Newton's mathematics let us predict planetary orbits, the fall of apples, the arc of cannonballs. We built bridges and calculated tides. We sent ships across oceans using stars as guides. The universe, it seemed, was knowable, smooth, continuous. But Newton never asked what space was made of. He never questioned whether it could be divided forever. He simply assumed, as most of us still do, that smoothness went all the way down. Then came Albert Einstein. In 1905, a young patent clerk in Switzerland published a paper that shattered Newton's absolute stage. Space and time, Einstein showed, were not separate. They were woven together into a single fabric space-time, and this fabric could bend. Gravity wasn't a force pulling objects together. It was the curvature of space-time itself. A planet orbiting a star wasn't being pulled. It was simply following the straightest possible path through curved space like a marble rolling around the rim of a bowl. It was one of the most beautiful ideas in the history of science. But here's the thing, Einstein's space-time was still smooth. His equations, the field equations of general relativity published in 1915, describe space-time as a flexible, continuous surface. It could warp and ripple and twist, but it never tore, it never pixelated, it never ended. Einstein used the mathematics of differential geometry, a language built entirely on the assumption of smoothness. Calculus itself, the tool that let him describe curves and changes, depends on the idea that you can always zoom in a little more, divide a little further. And it worked, brilliantly. In 1919, Arthur Eddington observed starlight bending around the sun during a solar eclipse exactly as Einstein predicted. Space-time, the universe confirmed, really does curve. In the decades that followed, general relativity passed every test. We discovered black holes, gravitational waves, the expansion of the universe, all described by Einstein's smooth, elegant equations. Today, GPS satellites orbiting Earth rely on general relativity. Time ticks slightly faster in orbit than on the ground because space-time is less curved up there. The difference is tiny, just 38 microseconds per day, but without correcting for it, your GPS would drift by miles within hours. Our entire technological civilization depends on Einstein's curved, smooth space-time. So, the question seems settled, doesn't it? Space-time is smooth. We've measured it, we've used it, we've trusted it. But some scientists began to whisper a different question. They asked, what if smoothness is just an approximation? What if at the smallest scales far tinier than atoms, far beyond anything we've ever measured, space-time stops being smooth? What if it frays? What if it foams? What if the fabric has a texture we've never seen? Think of it this way. If you look at a photograph from across a room, it appears perfectly smooth, a seamless image of faces, landscapes, light. But walk closer, closer still. Eventually, if the resolution is high enough, you'll see pixels, individual dots of color. The smoothness you realize was an illusion. It only existed because you were standing too far away. Now ask yourself, have we ever looked closely enough at space-time? The answer quietly is no. We've measured down to scales of about 10 to 18 meters, 1,000th of the size of a proton. At those scales, space-time still looks smooth. Particles still move through it, as if gliding on silk. But there's a scale we've never reached, a scale where the mathematics itself begins to tremble. It's called the Planck length 1.6 x 1035 meters. To give you a sense of how small that is, if an atom were the size of the entire observable universe, the Planck length would still be smaller than a single atom. At this scale, something strange happens. Quantum mechanics. The physics of the very small meets general relativity. The physics of gravity and space-time. And when they meet, the equations break. They return infinities, impossibilities. They whisper that our smooth, continuous space-time might not exist at all down there. They suggest that space and time themselves dissolve. Some scientists believe space-time at the Planck scale is a seething foam, a quantum froth of tiny bubbles, wormholes, and virtual black holes flickering in and out of existence faster than thought. Others believe it's woven from discrete threads, a network of quantum loops stitching reality together like fabric. Still others think space-time is made of vibrating strings, and at the smallest scales, those strings make the fabric shudder and tear. All of them agree on one thing: smoothness at the very bottom might be a lie we tell ourselves because we're too big to see the truth. And if that's true, if space-time really is granular, discrete, pixelated at its core, then everything changes. The Big Bang might not have been a singularity, a point of infinite density where the laws of physics collapse. It might have been a bounce moment where the universe compressed to the Planck scale and then rebounded. Black holes might not contain true singularities either. Their centers might be quantum foam, fuzzy and strange, but not infinite. Time itself might not flow. It might tick advancing in the smallest possible increments like frames in a film. Between one Planck moment and the next, there might be nothing. No time, no change. Just a gap in the sequence. Causality. The idea that every effect has a cause might fray at the edges. If time is discrete, what happens between moments? Does the universe pause? Or do we simply lack the language to describe what between even means when there is no between? These are not idle questions. They are questions that physicists have spent decades, lifetimes trying to answer. They are questions that mathematics whispers but cannot yet shout. They are questions that might change what it means to exist in space and time. And they all begin with a simple, quiet thought. What if the smoothness we see is only because we haven't looked closely enough? Tonight we're going to look. We'll visit the scientist who first saw the cracks, Max Planck, who discovered that energy comes in packets, not smooth streams. We'll walk with Einstein, who bent space-time but never broke it. We'll meet the modern physicists who dared to imagine space-time crumbling into foam or weaving itself from threads thinner than dreams. We'll examine the evidence faint indirect, but growing that space and time might have a texture. We'll look at gamma rays from distant galaxies, gravitational waves rippling through the cosmos, experiments at the edge of what's possible, all searching for the same thing, proof that the fabric beneath everything is not fabric at all. And we'll ask what it means for the universe, for us, for the way we understand reality itself. But we'll do it slowly, gently, one breath at a time, because the universe, it turns out, is patient. It's been hiding its deepest secrets for 13.8 billion years. It can wait a little longer while we drift through the questions. So, settle in. Let the world grow quiet. Let your thoughts soften at the edges. We're about to descend beneath the surface of everything, beneath matter, beneath energy, beneath the very grid on which existence rests. We're going to visit the place where smoothness ends and something stranger begins. The place where space itself might crumble. And who knows? Maybe in the search for the texture of reality, we'll find something even more beautiful than the smoothness we thought we knew. After all, every thread in a fabric is discrete, but together, woven carefully, they make something whole. Perhaps the universe works the same way. Let's find out. We begin, as all great questions do, by looking back, by understanding what we believed and why. For centuries, humanity built its understanding of reality on one quiet assumption that space and time were smooth, continuous, infinitely divisible. We never questioned it. We simply trusted the surfaces we walked on, the moments we lived, through the distances we measured. But trust, as it turns out, is not the same as truth. For thousands of years, we walked through the world believing in a simple truth, that between any 2 points there were infinite places to pause. That space could be divided forever. That if you cut a distance in half and then cut that half in half and kept cutting, you would never reach an end. It seemed obvious. After all, look at a line drawn on paper. Where does it stop being divisible? You can always imagine splitting it again, can't you? One more cut. One more fraction, one more infinitely small piece. This belief, this assumption of infinite smoothness, shaped everything we built. Our mathematics, our physics, our understanding of motion, distance, cause, and effect. But it began quietly with a paradox that no one could solve. Around 450 BCE, in the Greek colony of Elea, a philosopher named Zeno proposed a puzzle. He wasn't trying to deny that motion existed. He could see people walking arrows, flying chariots, racing. But he wanted to show that motion. As we understand, it shouldn't be possible. Here's what he said. Imagine you want to walk from one side of a room to the other. Simple enough, right? But before you reach the far wall, you must first reach the halfway point. And before you reach that halfway point, you must reach the point halfway to that. And before that, halfway again. Each journey contains an infinite number of smaller journeys. To cross a room, Zeno argued you would need to complete an infinite number of steps, and completing infinity should take forever. Yet somehow we cross rooms every day. Zeno called this the dichotomy paradox. It wasn't a joke, it was a serious challenge to the Greek understanding of space and motion. If space is infinitely divisible, he suggested then motion itself becomes impossible to explain. You would be forever stuck trying to finish an endless sequence of smaller and smaller distances. Another of his paradoxes was even more famous: Achilles and the tortoise. Imagine Achilles, the fastest runner in Greece, racing a tortoise. Being generous, he gives the tortoise a head start, say 100 meters. The race begins. Achilles runs swiftly toward the tortoise, but by the time he reaches the spot where the tortoise started, the tortoise has moved a little farther ahead, maybe 10 meters. No problem. Achilles runs to that new spot. But again, by the time he arrives, the tortoise has crept forward perhaps 1 meter. Achilles closes the gap again, but the tortoise moves again, and again, and again. Logically, Zeno said, Achilles must always close the distance the tortoise has gained, but the tortoise will always have moved a tiny bit farther. Therefore, Achilles can never overtake the tortoise. Of course, in reality, Achilles would fly past the tortoise in seconds. But Zeno wasn't describing reality. He was exposing a flaw in how we think about infinity and continuity. Greek philosophers argued about Zeno's paradoxes for centuries. Some tried to dismiss them as word games. Others saw them as proof that motion was an illusion, that reality was actually static and unchanging beneath the surface. Aristotle in the 4th century BCE tried to resolve them by distinguishing between potential infinity and actual infinity, saying that space could potentially be divided forever, but you never actually complete infinite divisions. It was a clever answer, but it didn't quite solve the deeper question: is space really continuous, or does it end somewhere at some smallest, unsplittable unit? Most chose to believe in continuity. It felt intuitive. It felt right. And so, for the next 2,000 years, humanity built its understanding of the universe on that assumption. By the 1600s, mathematics had become powerful enough to describe motion with precision. Galileo Galilei, observing balls rolling down inclined planes, discovered that objects accelerate smoothly and predictably. He didn't need to worry about infinite divisions. He simply measured distances and times, and the math worked beautifully. Then Isaac Newton arrived. In 1687, Newton published Philosophia Naturalis Principia Mathematica, arguably the most important book in the history of science. In it, he laid out his laws of motion and universal gravitation. He showed that the same force that pulls an apple to the ground also holds the moon in orbit around Earth and Earth in orbit around the sun. It was a universe unified by mathematics. But Newton's universe depended on something even more fundamental: absolute space and absolute time. Space, Newton said, was like an infinite invisible grid stretching in all directions, perfectly flat, perfectly still, unchanging. It existed whether anything occupied it or not. It was the stage on which the universe performed. Time, he said, flowed uniformly everywhere. A second on Earth was a second on Jupiter, a second in the farthest star. Time didn't speed up or slow down. It simply was a river flowing at the same rate for all observers forever. Newton's visions was clean, elegant, absolute, and crucially, it was smooth. In his framework, you could measure any distance no matter how small. You could measure any duration no matter how brief. There was no smallest unit, no fundamental grain. Space and time were continuous, infinitely divisible, perfectly smooth. And the mathematics he invented, calculus, was built entirely on that idea. Calculus, co-invented by Newton and Gottfried Wilhelm Leibniz in the late 1600s, is the mathematics of smooth change. It lets you calculate the slope of a curve at a single point, the area under a flowing line, the rate at which something accelerates or decays. But here's the key: calculus only works if you assume continuity. To find the instantaneous velocity of a moving object, you imagine dividing time into smaller and smaller intervals, approaching zero, but never quite reaching it. You assume that between any two moments, there are infinite moments in between. You assume smoothness all the way down. And it worked, spectacularly. Newton used calculus to predict planetary orbits with stunning accuracy. Edmund Halley used it to calculate the return of a comet, the comet we now call Halley's Comet, decades before it reappeared in 1758 exactly as predicted. Engineers use calculus to design bridges, calculate trajectories, understand the motion of fluids. The universe, it seemed, was smooth. The math proved it. For over 200 years, Newtonian mechanics reigned. Scientists mapped the solar system, discovered new planets, measured the speed of light. They built steam engines and railroads. They calculated eclipses centuries in advance. The universe operated like a vast, perfect clock, smooth, predictable, deterministic. If you knew the position and velocity of every particle in the universe, the French mathematician Pierre-Simon Laplace famously claimed in 1814, you could predict the entire future and reconstruct the entire past. Past, present, and future were just different locations along the smooth, continuous timeline of absolute Newtonian time. It was a comforting vision, a universe that made sense. But no one asked, what is space made of? No one asked, why is time continuous? They simply assumed, because it worked, because it felt true. Then at the turn of the 20th century, everything shattered. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published 4 papers that changed physics forever. One of them introduced the world to special relativity. Albert Einstein showed that space and time were not separate absolute things. They were woven together into a single flexible fabric space-time. And this fabric behaved in ways Newton never imagined. Time, Einstein revealed, does not flow at the same rate everywhere. If you move very fast, close to the speed of light, time slows down for you relative to someone standing still. If you travel in a rocket at 90%, the speed of light for 1 year, you might return to Earth to find that 10 years have passed for everyone else. This isn't science fiction. It's been measured. Atomic clocks flown on airplanes tick slightly slower than identical clocks on the ground. Particles called muons created high in Earth's atmosphere shouldn't survive long enough to reach the surface, but they do, because time moves slower for them as they travel at near light speed. Space, too, is not absolute. Distances shrink when you move quickly. A spaceship traveling at relativistic speeds becomes shorter, actually physically shorter, along the direction of motion. Not because it's compressed by some force, but because space itself contracts. Einstein's equations showed that space and time are relative, malleable, flexible, intertwined. But here's the crucial point. Einstein's space-time was still smooth. 10 years later, in 1915, Einstein expanded his theory into general relativity. He showed that gravity wasn't a force pulling objects together. It was the curvature of space-time itself. Massive objects like stars and planets bend space-time around them, the way a heavy ball placed on a stretched rubber sheet creates a dip. Other objects moving nearby follow the curves, not because they're being pulled, but because they're simply traveling along the straightest possible paths through curved space. It's one of the most beautiful ideas in all of science, and it's been confirmed again and again. In 1919, during a solar eclipse, astronomers observed starlight bending around the sun exactly as Einstein predicted. In 2015, scientists detected gravitational waves, for the first time ripples in space-time created by colliding black holes 1.3 billion light-years away. In 2019, we photographed the shadow of a black hole, its gravity bending light into a glowing ring. General relativity works perfectly. And it depends entirely on smooth, continuous space-time. Einstein's field equations describe how matter and energy curve space-time. But those equations are written in the language of differential geometry, a mathematics built on calculus, built on the assumption that space and time can be divided infinitely smoothly without end. At every scale we've ever measured, space-time behaves exactly as general relativity predicts. The global positioning system. The GPS in your phone relies on it. Satellites orbit Earth at about 20,000 kilometers above the surface, where space-time is less curved than it is on the ground. As a result, time ticks slightly faster up there, about 38 microseconds per day, faster than clocks on Earth. That sounds tiny. But if we didn't correct for it, GPS would drift by about 10 kilometers per day. Within a week, your navigation would be useless. So, we correct for it. We adjust the satellite clocks to account for relativistic time dilation, and it works flawlessly. Every single day, billions of people trust their lives to Einstein's smooth curve space-time. It seems settled, doesn't it? Space-time is smooth, we've measured it, we've used it, we've built a technological civilization on top of it. But some scientists began to ask a different question. A quieter question. What if smoothness is just an approximation? What if general relativity works so well because we've only ever tested it at relatively large scales? Scales where the underlying texture, if it exists, averages out into smoothness, the way pixels in a photograph blend together when viewed from a distance. What if at the smallest scales, scales far tinier than atoms, far beyond anything we've ever directly measured, space-time stops obeying Einstein's equations? What if it frays, foams, pixelates? What if beneath the smooth surface we trust, there's something grainier, stranger, more fundamental? It's not a new question. In fact, hints of it appeared almost as soon as Einstein published general relativity. Because there was one place where Einstein's smooth space-time broke down completely singularities. At the center of a black hole, general relativity predicts that space-time curves infinitely. Density becomes infinite. The equations return nonsense division by zero, infinite values, mathematical impossibilities. Einstein himself was deeply uncomfortable with this. Singularities, he felt, suggested that his theory was incomplete, that it was only an approximation of something deeper. And he was right. Because in the early 1900s, at the same time, Einstein was bending space-time, another revolution was unfolding. A revolution that suggested the universe wasn't smooth at all. It was called quantum mechanics, and it would shatter the assumption of continuity forever. But that discovery didn't come from questions about space and time. It came from something simpler, something no one expected: the color of heated metal glowing softly in a darkened laboratory. In the winter of 1900 in Berlin, a physicist named Max Planck was trying to solve a problem that shouldn't have been a problem at all. He was studying something simple: the light emitted by heated objects. When you heat metal, iron, steel, anything, it glows. First red, then orange, then yellow, then white as it gets hotter. This glow is called blackbody radiation, and every object with temperature emits it, including you right now, glowing softly in infrared. The problem was that the equations didn't work. According to classical physics, Newton's physics, the physics of smooth, continuous energy, a heated object should emit infinite amounts of energy at short wavelengths. Heat something up, and it should flood the room with ultraviolet light, X-rays, gamma rays, everything. Infinite energy pouring out of a simple hot stove. It was called the ultraviolet catastrophe. And it made no sense because obviously a hot stove doesn't incinerate you with gamma rays. It just glows. Planck tried every equation he knew. Nothing worked. Finally, in what he later called an act of desperation, he made a strange assumption. He assumed that energy wasn't continuous. He assumed it came in tiny, discrete packets like coins instead of water. He called these packets quanta, and when he used this assumption, the equations worked perfectly. On December 14th, 1900, Planck presented his solution to the German Physical Society. He calculated the size of these energy packets using a new constant now called Planck's constant, H Shams 6.626 x 10^34 joule seconds. It's an absurdly small number. In everyday life, energy appears smooth because these packets are so tiny we can't distinguish them. It's like trying to see individual grains of sand on a beach from an airplane. They blur into smoothness. But they're there. Planck himself didn't believe it was real. He thought it was just a mathematical trick, a convenient fiction that happened to match the data. For years, he tried to find a way to explain black-body radiation without quanta. He failed. Because the universe, it turned out, really is granular. 5 years later, in 1905, Albert Einstein took Planck's idea more seriously than Planck himself did. Einstein was working on a different puzzle, the photoelectric effect. When you shine light on certain metals, they emit electrons. Simple enough? But here's the strange part. If you increase the brightness of the light, you get more electrons, but each electron has the same energy. If you want higher energy electrons, you don't use brighter light. You use light with a shorter wavelength. Blue light works better than red light, no matter how bright the red light is. Classical physics couldn't explain this. If light were a smooth, continuous wave, as everyone believed, then brighter light should mean more energy per electron. But it didn't. Einstein proposed something radical. Light itself comes in packets, discrete particles of energy, quanta of light. We now call them photons. Each photon carries energy proportional to its frequency. Blue light photons carry more energy than red light photons. When a photon hits an electron, it transfers all its energy or none. There's no in-between. It's all or nothing. Discrete. Einstein's paper on the photoelectric effect earned him the Nobel Prize in 1921. But more importantly, it confirmed what Planck had suspected: energy at its most fundamental level is not smooth. It's granular. It comes in indivisible chunks. The universe, in other words, has a resolution limit. For a while, physicists tried to contain the strangeness. Maybe energy is quantized, they thought, but space and time are still smooth. Maybe atoms emit light in discrete packets, but the atoms themselves move continuously through space. Then, Niels Bohr shattered that hope. In 1913, Bohr was studying the hydrogen atom, the simplest atom, just one proton and one electron. According to classical physics, the electron should orbit the proton, like a planet orbits the sun, spiraling inward as it radiates energy, eventually crashing into the nucleus. But atoms don't collapse. They're stable. Bohr proposed something shocking. Electrons can only exist in certain orbits at certain specific distances from the nucleus. Not anywhere in between, just certain allowed states like rungs on a ladder. An electron in a hydrogen atom can be in the first orbit, or the second orbit, or the third. But it cannot be halfway between the first and second. There is no halfway. When an electron jumps from one orbit to another, it doesn't travel through the space in between. It simply disappears from one orbit and reappears in another, emitting or absorbing a photon in the process. This was heresy. Motion was supposed to be smooth, continuous. But Bohr was saying that at the atomic level, motion isn't smooth at all. It's discontinuous, quantum. And once again, the equations worked. Bohr's model predicted the exact wavelengths of light emitted by hydrogen atoms, wavelengths that had been measured with extraordinary precision for decades but never explained. The universe was revealing itself piece by piece as fundamentally granular. But the strangest discovery was still to come. In 1927, Werner Heisenberg, a 25-year-old physicist in Germany, derived a principle that would become one of the most famous and most misunderstood ideas in all of science. It's called the uncertainty principle. Heisenberg showed that there's a fundamental limit to how precisely you can know certain pairs of properties at the same time. The most famous example position in momentum. The more precisely you know where a particle is, the less precisely you can know how fast it's moving, and vice versa. This isn't because our instruments are imperfect. It's not because we're clumsy or our measurements disturb the particle. It's because at the quantum level, particles don't have precise positions and momenta simultaneously. It's not that we don't know, it's that the universe itself doesn't know. These properties are fundamentally fuzzy, fundamentally uncertain, fundamentally not smooth. The uncertainty is built into reality. Heisenberg calculated the minimum uncertainty using Planck's constant. For position and momentum, the product of their uncertainties must be at least h2, where h bar is Planck's constant divided by 2p, about 1.055 x 1034 joule seconds. Again, an absurdly small number. In everyday life, this uncertainty is negligible. You can know where your car is and how fast it's moving, with no practical uncertainty at all. But for an electron, for a photon, the uncertainty is everything. An electron in an atom doesn't have a precise location. It exists as a cloud of probability smeared out across space. Only when you measure it does it collapse into a definite position, and even then, only for that instant. It's as if reality itself refuses to be pinned down. And there's more. Heisenberg's principle also applies to energy and time. The more precisely you try to measure the energy of a particle, the less precisely you can define when that energy existed. At the smallest time scales around 10 to 43 seconds called the Planck time, the uncertainty in energy becomes so large that the universe itself becomes blurry. Particles can borrow energy from the vacuum, pop into existence for an instant, and vanish again as long as they do it quickly enough that the uncertainty principle allows it. These are called virtual particles, and they're everywhere, constantly flickering in and out of existence in what's called the quantum vacuum. Space at the smallest scales is not empty. It's seething, foaming, alive with particles that exist for the briefest moments before disappearing. Smoothness at this level is gone. By the 1930s, quantum mechanics was complete. Scientists like Erwin Schrödinger, Paul Dirac, Wolfgang Pauli, and Max Born had built a mathematical framework that described the quantum world with stunning accuracy. It predicted the behavior of atoms, the structure of molecules, the properties of light, and every prediction came true. Quantum mechanics is the most successful scientific theory ever created. It's the foundation of chemistry, electronics, lasers, transistors, computer chips, MRI machines. The device you're using to watch this video right now, whether it's a phone, tablet, or computer, exists because we understand quantum mechanics. But here's the unsettling part. Quantum mechanics reveals that reality at its core is not smooth. It's granular, probabilistic, uncertain. Matter is made of atoms. Atoms are made of electrons, protons, and neutrons. Protons and neutrons are made of quarks. Quarks and electrons are, as far as we know, fundamental indivisible. Energy comes in photons. Photons are indivisible packets of light. You can't have half a photon. You can't have 1.5 photons. You have one or two or none. Action. The product of energy and time comes in units of Planck's constant. There's no smaller action possible. The universe has a smallest unit of doing. And this raises the question we've been circling. If matter is granular, if energy is granular, if action is granular, is space-time granular too? Most physicists in the early 20th century assumed not. They thought space-time was still smooth, still continuous, still infinitely divisible, even if the things moving through it weren't. But a few began to wonder. In 1930, a physicist named Lev Landau suggested that space itself might have a discrete structure at very small scales. In the 1940s, Hartland Snyder and others explored the idea of quantized space-time. In 1955, John Archibald Wheeler, one of the great visionaries of 20th century physics, coined a term for what space-time might look like at the Planck scale. He called it quantum foam. Wheeler imagined that at distances around 1035 meters, space-time doesn't look smooth at all. It's a churning, bubbling froth of quantum fluctuations, tiny wormholes, virtual black holes, microscopic tears in the fabric of reality, all flickering in and out of existence faster than anything can traverse them. At this scale, he suggested the very concepts of distance and time lose meaning. Geometry itself dissolves into probability. It was a poetic vision, a strange vision. And for decades it remained purely speculative because no one could figure out how to test it. But the idea wouldn't go away. Because quantum mechanics and general relativity, the two pillars of modern physics, were incompatible. General relativity describes gravity as the smooth curvature of space-time. It works beautifully at large scales, planets, stars, galaxies, black holes. Quantum mechanics describes the behavior of particles at tiny scales. It works beautifully for electrons, photons, atoms. But when you try to combine them, when you try to describe what happens to space-time at quantum scales, the equations break. They produce infinities nonsense mathematical impossibilities. The problem is, this quantum mechanics says the vacuum is never truly empty. It's full of fluctuating fields, virtual particles, constant uncertainty. At the Planck scale, these fluctuations become violent. Energy density fluctuates wildly. And in general relativity, energy curves space-time. So if energy is fluctuating violently, space-time should be fluctuating violently too, curving, twisting, tearing, foaming. But smooth space-time can't handle that kind of violence. The math collapses. It suggests that at the Planck scale, space-time as we know it, smooth, continuous geometrical, ceases to exist. Something else must take its place. Scientists have spent nearly a century trying to figure out what that something is. Some believe space-time is woven from discrete quantum threads. Others believe it emerges from vibrating strings. Still others believe it's a network of relationships or a hologram or something we don't even have words for yet. But they all agree on one thing. If quantum mechanics is correct, and it is spectacularly then, space-time cannot be smooth all the way down. At the smallest scales, smoothness must break. The universe, it turns out, is not a photograph that you can zoom into forever. It's a digital image. And if you zoom in far enough, you'll find pixels. The question is, what are those pixels made of? And can we ever see them? Because here's the problem. The Planck scale is unimaginably small. An atom is about 10 meters across. A proton is about 10-15 meters. The smallest distance we've ever probed directly is about 10 to 19 meters using the Large Hadron Collider. But the Planck length is 1035 meters. That's a million billion times smaller than anything we've ever measured. To build a particle accelerator powerful enough to probe the Planck scale directly, you'd need a machine larger than the solar system, consuming more energy than the sun produces in a year. We can't see the graininess of space-time. Not directly, possibly not ever. But the mathematics whispers that it's there. The equations insist that smoothness must end. And a few clever scientists have begun to think of indirect ways to search for it. Faint echoes, tiny hints, shadows cast by a texture too small to see. There's a number hidden in the fabric of reality, a number so small that writing it out feels almost meaningless. And yet, it might be the most important measurement in all of physics. It's called the Planck length 1.61625 x 1035 meters. To understand how small this is, imagine an atom. Atoms are already inconceivably tiny, about 10 to 10 meters across, so small that you could fit billions of them on the tip of a pin. Now take that atom and shrink it down by the same ratio that the atom is smaller than the entire observable universe. You're not even close to the Planck length yet. The Planck length is to an atom what an atom is to a region of space about 100,000 light years, across roughly the diameter of our entire galaxy. It's a scale so small that comparing it to anything in the human world becomes absurd. And yet this number was calculated over a century ago by a man who had no idea what it truly meant. In 1899, Max Planck, the same physicist who discovered energy, comes in quanta, was playing with fundamental constants. He was looking for a way to define units of measurement that didn't depend on human conventions like meters or seconds units that would be the same anywhere in the universe for any observer. He took three constants: the speed of light, c, the gravitational constant, g, and his newly discovered Planck constant, h, and he combined them mathematically. What he found were natural units, fundamental scales built into the universe itself. The Planck length GC3, 1.6 to C10 to 35 meters. The Planck time GC5, 5.4 1044 seconds. The Planck mass CG 2.2 at 10 to 8 kilograms, about the mass of a flea egg. The Planck energy C5G 1.96 x 109 joules. Roughly the energy of a car traveling at highway speed. Planck didn't know what these numbers meant. He thought they were just curiosity's abstract combinations of constants. He couldn't have imagined that they represented the fundamental limits of reality itself. But they do. The Planck length isn't just small, it's the scale where space itself, the very concept of distance, begins to lose meaning. Here's why. In quantum mechanics, Heisenberg's uncertainty principle tells us that the more precisely you try to measure the position of a particle, the more uncertain its momentum becomes. To measure something very precisely, you need to probe it with very high-energy particles with very short wavelengths, but in general relativity energy curves, space-time. And if you concentrate enough energy into a small enough region, that energy itself will curve space-time so much that it creates a black hole. So, imagine trying to measure a distance smaller than the Planck length. To do that, you'd need to use particles with wavelengths shorter than 1035 meters. But particles with wavelengths that short carry so much energy, Planck scale energy, that they would collapse into tiny black holes. And those black holes would have event horizons larger than the distance you're trying to measure. You can't measure distances smaller than the Planck length because the act of measurement itself destroys the space you're trying to probe. It's not a technological limitation. It's a fundamental limit built into the laws of physics. The Planck length, in other words, might be the smallest meaningful distance in the universe. Below it, the very concept of distance dissolves. The same is true for time. The Planck time, 5.4 x 10 to 44 seconds, is the time it takes light to travel one Planck length. It's the shortest interval of time that can even in principle be measured or have any physical meaning. To put this in perspective, there are more Planck times in 1 second than there have been seconds since the Big Bang. About 10 to 44 Planck times fit into a single second. The age of the universe, the 13.8 billion years, is only about 117 seconds. The difference is incomprehensible. If you could experience time at the Planck scale, a single second of your life would feel longer than the entire history of the universe. But nothing experiences time at the Planck scale, because at that scale time itself might not exist as a continuous flow. Think of it this way. If you watch a movie, the motion looks smooth. Characters walk, cars drive, clouds drift across the sky. But a movie is made of individual frames, typically 24 frames per second. Between each frame, there's nothing. No motion, no change, just a gap. Yet your brain stitches those frames together into the illusion of continuous motion. Some physicists believe time works the same way. At large scales, at human scales, time appears to flow smoothly. But at the Planck scale, it might be discrete. Time might advance in tiny, indivisible ticks, like frames in a film. And between those ticks, there is no between. There is simply nothing. This idea that space-time itself is fundamentally discrete is called quantum space-time. And if it's true, it changes everything. In 1955, the physicist John Archibald Wheeler began seriously thinking about what space-time would look like at the Planck scale. Wheeler was a giant of 20th century physics. He coined the term black hole. mentored Richard Feynman, and spent decades exploring the deep connections between quantum mechanics and gravity. Wheeler imagined zooming in on empty space, getting smaller and smaller, past atoms, past protons, past quarks, all the way down to the Planck scale. What he envisioned was chaos. At the Planck scale, Wheeler suggested spacetime doesn't look like smooth fabric. It looks like foam, quantum foam, a seething, churning froth of virtual particles, tiny wormholes, microscopic black holes, all popping in and out of existence faster than light can cross them. The uncertainty principle allows this. Energy can be borrowed from the vacuum as long as it's paid back quickly enough. At the Planck scale, the borrowed energy is enormous, and the time scale is so short that space-time itself fluctuates wildly. Imagine looking at the surface of the ocean from an airplane. It looks smooth, glassy, calm. But dive beneath the surface and you find currents, eddies, turbulence. Dive deeper still, and you find molecules of water jostling against each other, held together by fleeting electromagnetic bonds. Wheeler suggested space-time is the same. At large scales, it looks smooth. But at the Planck scale, it's alive foaming, constantly reshaping itself. Geometry. The very idea of here and there becomes probabilistic. Distances flicker, angles shift. Topology itself, whether space is connected or torn, becomes uncertain. Wheeler called this the quantum geometry of spacetime, and he realized something profound. If spacetime is fundamentally quantum, then the universe doesn't sit on spacetime. The universe is spacetime. There's no stage beneath the actors. The stage is woven from the same quantum threads as everything else. But Wheeler couldn't prove it. No one could. The Planck scale was, and still is, completely beyond our ability to probe directly. To give you a sense of the challenge, the Large Hadron Collider, the most powerful particle accelerator ever built, can probe distances down to about 10-19 meters. That's extraordinarily small, a billionth of a meter. But the Planck length is 1035 meters. That's a quadrillion times smaller, a million billion times smaller than what the LHC can reach. To build a particle accelerator powerful enough to directly probe the Planck scale, you'd need a machine with a circumference roughly the size of the Milky Way galaxy. It would require more energy than the sun produces in millions of years. It's not just impractical, it's impossible with any technology we can imagine. So, we've never seen space-time at the Planck scale. We've never measured it directly. Everything we know about it comes from mathematics, from combining quantum mechanics and general relativity and seeing what the equations whisper. And they whisper something strange. They whisper that at the Planck scale, the smooth space-time of Einstein's equations ceases to exist. It fractures, pixelates, foams. But here's the thing that's easy to misunderstand. This doesn't mean space-time is made of tiny Planck-length cubes like Lego blocks stacked together. It's subtler than that. It means that below the Planck scale, the very questions we ask stop making sense. Asking, what's the distance between these 2 points, becomes meaningless, like asking what's north of the North Pole. The question assumes a concept of direction that doesn't exist beyond a certain boundary. At the Planck scale, distance itself might not be a fundamental property. It might be something that emerges, something that appears only when you zoom out, when you average over many quantum fluctuations, when the foam settles into something that looks smooth from a distance. Think of a beach. From far away, the sand looks like a smooth, continuous surface. But walk closer, and you see individual grains. Each grain is discrete, separate. The smoothness was an illusion created by distance. But now, imagine something stranger. Imagine the grains of sand are constantly rearranging themselves faster than you can blink. Imagine they're not solid objects, but probabilities flickering in and out of existence, sometimes here, sometimes there, sometimes nowhere at all. That's closer to what space-time might be like at the Planck scale. And if that's true, then some of the deepest mysteries in physics might suddenly make sense. Take the Big Bang, for example. In standard general relativity, if you trace the universe backward in time, it gets smaller and smaller, denser and hotter, until about 13.8 billion years ago. It reaches a singularity, a point of infinite density, infinite temperature, infinite curvature, a place where the equations break down completely and return nonsense. Einstein himself hated singularities. He thought they were a sign that general relativity was incomplete, that it was only an approximation of something deeper. And he was right. Because if space-time is quantized, if the Planck length is the smallest possible distance, then the singularity disappears. The universe can't compress to a point of infinite density, because there is no point smaller than the Planck scale. Instead, the universe compresses down to a Planck scale volume, unimaginably tiny, but not zero, not infinite. Some theories suggest that at this scale, quantum effects become so strong that they create a kind of repulsive force, causing the universe to bounce instead of collapsing into a singularity. The Big Bang wasn't the beginning. It was a transition, a moment, when a previous collapsing universe reached the Planck scale and rebounded into expansion. This is called loop quantum cosmology, and it's one of the most elegant ideas in modern physics. It eliminates the singularity. It says the universe has no true beginning, only cycles of contraction and expansion, each bounce occurring at the Planck scale, where quantum space-time takes over. Black holes, too, might lose their singularities. In general relativity, the center of a black hole is predicted to be a singularity, a point where space-time curvature becomes infinite, where density becomes infinite, where physics breaks. But if space-time is quantized, the singularity disappears there too. The center of a black hole might be a Planck scale region of quantum foam, strange, yes, but not infinite, not impossible. This could solve one of the biggest problems in theoretical physics, the black hole information paradox. If information falls into a singularity, it's lost forever, which violates quantum mechanics. But if there's no singularity, only a Planck scale quantum core, then information might be preserved encoded in the quantum structure of space-time itself. We don't know if any of this is true, but the Planck scale is where these questions live. And here's the haunting part: we might never know for sure. The Planck scale might be forever beyond direct observation. It's a boundary written into the universe itself, a place where the tools we use to measure reality become meaningless, where the very concepts of space and time dissolve into quantum uncertainty. It's the edge of knowability, and yet scientists keep searching, not by building impossible accelerators, but by looking for indirect effects. Tiny echoes, faint shadows, subtle hints that space-time has a texture too small to see, but large enough perhaps to leave traces in the signals that reach us from the farthest edges of the universe. Imagine you're holding a piece of fabric silk, perhaps, or linen. From a distance it looks perfectly smooth, continuous whole, but bring it closer. Look carefully. You'll see threads, individual strands woven together in a pattern, crossing and looping, creating the illusion of smoothness through their collective structure. Now, imagine something stranger. Imagine the threads themselves are not made of anything. They don't exist in space. They are space. Remove the threads, and there is no emptiness left behind because space itself was the weaving. This is the vision at the heart of one of the most radical ideas in modern physics. It's called loop quantum gravity, and it suggests that space, the thing we move through, the thing we trust to be continuous and smooth, is actually woven from quantum threads so tiny that they exist at the Planck scale, threads that loop and connect and twist to create the fabric of reality itself. The story begins in the 1980s when three physicists, Abhay Ashtekar, Carlo Rovelli, and Lee Smolin, started asking a question that most scientists had been avoiding. What if we take quantum mechanics seriously and apply it directly to space-time itself? Not to particles moving through space-time, not to fields existing in space-time, but to space-time as a thing unto itself. This was a strange idea. Most attempts to combine quantum mechanics and gravity had focused on treating gravity as a force like electromagnetism and trying to build a quantum theory of gravitational particles called gravitons. But Ashtekar, Rovelli, and Smolin took a different path. They returned to Einstein's insight. Gravity isn't a force, it's the curvature of space-time. So if you want to quantize gravity, you have to quantize space-time itself. You have to break space into pieces. By the early 1990s, they had developed the mathematical framework. And what emerged was beautiful, strange, and profoundly different from anything physicists had imagined. In loop quantum gravity, space is not a smooth continuum. It's a network, a quantum network made of discrete building blocks. These building blocks are called spin networks. A spin network is a graph, a collection of nodes connected by edges like a web. Each edge represents a quantum of space, a thread of geometry, carrying a specific amount of area. Each node represents a connection where 3 or more threads meet, where the geometry of space is woven together. The edges are not embedded in space. They are space. There is no background, no stage, just the network itself. And the surprising thing is, the edges are quantized. They come in discrete sizes. Area, the fundamental measure of a two-dimensional surface, is quantized in loop quantum gravity. You can't have any arbitrary area. You can only have certain specific values determined by multiples of the Planck area, about 2.6 x 1070 square meters. It's like saying area comes in pixels, and the pixels are unimaginably tiny. To give you a sense of scale, if you took the surface of a sphere the size of a proton and tried to measure its area in Planck units, you'd find it contains about 10^140 Planck area pixels. That's 10 trillion pixels on the surface of a single proton. And yet those pixels are there. The math insists on it. Volume is quantized too. In loop quantum gravity, the smallest possible volume is about 4x 10^105 cubic meters, a Planck volume. You can't have half a Planck volume. You can't have 0.3 Planck volumes. You have 1 or 2 or none. This is radical. It means space itself is fundamentally discrete, fundamentally grainy, fundamentally not infinitely divisible. Zeno was wrong. You can't divide space forever. Eventually, you reach the quantum threads, and there's nothing smaller to divide. But here's where it gets even stranger. Time in loop quantum gravity is not fundamental. In our everyday experience, time flows. It ticks forward second by second, carrying us from past to future. We think of time as a dimension, just like space, a coordinate, a direction, a thing that exists independently. But Carlo Rovelli, one of the founders of loop quantum gravity, argues that time is an illusion, not in a mystical sense, but in a precise physical sense. At the Planck scale, Rovelli suggests there is no time. There are only quantum states configurations of the spin network and transitions between them. Time emerges from the sequence of changes in the network. It's not a river we move through. It's the experience of change itself. Think of it this way. Imagine a deck of cards. You shuffle it, and the order changes. Did time pass? Only in the sense that the configuration changed. The cards themselves don't experience time. They just exist in different arrangements. Rovelli suggests the universe works the same way. At the fundamental level, there's no flowing time, just a sequence of quantum states, each slightly different from the last. And we living within that sequence perceive those changes as the passage of time. This idea called timelessness, or the problem of time, has haunted quantum gravity for decades. But in loop quantum gravity, it's not a bug, it's a feature. Because if time is not fundamental, then the universe doesn't evolve in time. It simply is a vast web of quantum relationships, frozen in a kind of eternal now, with change encoded in the structure itself. It's a vision that would have astonished Newton, and maybe even Einstein. But does it work? Can loop quantum gravity actually describe the universe we see? The answer is partially. One of loop quantum gravity's greatest successes is that it eliminates singularities. Remember, in general relativity, singularities are places where space-time curvature becomes infinite, like the center of a black hole or the Big Bang. The equations break down, physics stops working. But in loop quantum gravity, singularities can't exist. Here's why, in general relativity, matter can be compressed to a point zero volume infinite density. But in loop quantum gravity, volume is quantized. There's a smallest possible volume, the Planck volume. You can't compress matter beyond that. When you apply loop quantum gravity to cosmology, the study of the entire universe, something remarkable happens. The Big Bang singularity disappears. Instead, the universe reaches a minimum volume about 1 Planck volume and then bounces. This is called the Big Bounce. In 2001, a physicist named Martin Bojewald used loop quantum gravity to model the very early universe. He found that as you trace the universe backward in time, it contracts, getting smaller and denser. But instead of collapsing into a singularity, quantum effects, specifically, the discreteness of space create a kind of repulsive force. The universe compresses to a Planck scale volume, then rebounds into expansion. The Big Bang in this picture wasn't the beginning of time. It was a transition, a moment when a previous collapsing universe reached its quantum limit and bounced back. This solves one of cosmology's deepest problems. What happened before the Big Bang loop? Quantum cosmology answers there was a before. The universe might be eternal, cycling through contractions and expansions, each bounce occurring at the Planck scale where quantum space-time takes over. Black holes, too, lose their singularities in loop quantum gravity. In general relativity, if you fall into a black hole, you eventually reach the singularity at the center, a point of infinite density where space-time curvature becomes infinite and the laws of physics collapse. But loop quantum gravity says not quite. At the Planck scale, the black hole's core becomes a region of quantum geometry, a tangle of spin network threads. Density is enormous, yes, but not infinite. Curvature is extreme, but not impossible. And because the singularity is gone, information that falls into the black hole might be preserved in the quantum structure of the core. This could resolve the black hole information paradox, one of the biggest unsolved problems in theoretical physics. Stephen Hawking showed in the 1970s that black holes emit radiation and eventually evaporate. But if information is lost in the singularity, quantum mechanics is violated. Loop quantum gravity suggests the information isn't lost. It's encoded in the discrete quantum geometry at the Planck scale. But here's the challenge. Loop quantum gravity is extraordinarily difficult to work with mathematically. The equations are complex, and extracting predictions for real-world experiments has proven nearly impossible. For decades, critics have argued that loop quantum gravity doesn't make testable predictions. It's mathematically beautiful, philosophically elegant, but practically untestable. And they have a point. The problem is that quantum gravitational effects only become significant at the Planck scales, so small we can't directly probe them. At larger scales, loop quantum gravity smoothly reduces to general relativity, which we already know works perfectly. So, how do you test it? One possibility is cosmology. If the universe really did bounce at the Planck scale, there might be traces left in the cosmic microwave background, the faint afterglow of the Big Bang. Some researchers have searched for unusual patterns in the CMB that might indicate a bounce. So far, the data is inconclusive. Another possibility is black holes. If black holes have Planck-scale quantum cores instead of singularities, their behavior might differ slightly from what general relativity predicts, especially during mergers when gravitational waves are emitted. LIGO and future gravitational wave detectors might be sensitive enough to see these differences, but so far no one has found definitive evidence. And yet loop quantum gravity persists, because it offers something profound, a vision of space-time that's both quantum and geometric, discrete and relational, fundamentally woven rather than fundamentally smooth. In this picture, the universe is not a container. It's a network. And everything we are, everything we see are patterns in that network, vibrations in the weaving. There's something almost poetic about it. Space is not emptiness, it's connection. Every Planck-length thread links to others, creating the structure we call distance, the flow we call time. Remove the threads and nothing remains, not even void, because the void itself was the threads. It's a vision that challenges our deepest intuitions. We think of space as a stage, a background, a place where things happen. But loop quantum gravity says no. Space is not the stage, space is the actors. The relationships between quantum states are the geometry. It's a universe built from the inside out. And if it's true, if space really is woven from discrete quantum loops, then the smoothness we experience is an illusion of scale. Stand far enough back and the weaving blurs into continuity. But zoom in and you find the threads. Discrete, quantum, real. Of course, loop quantum gravity isn't the only answer. There's another path, another way to imagine how space-time might break apart at the smallest scales. A path that starts not with geometry, but with vibrations. What if everything, every particle, every force, every interaction in the universe is just music, not metaphorically, literally? What if the electron in your body, the photon carrying light to your eyes, the quarks holding atomic nuclei together? What if they're all just different notes played by the same fundamental instrument, different vibrations of something deeper, something smaller, something that exists at the very edge of reality? This is the central idea of string theory, and it offers a completely different answer to the question of what space-time looks like at the Planck scale. Where loop quantum gravity imagines space as a network of discrete quantum threads, string theory imagines something stranger, that the fundamental building blocks of reality aren't particles at all. They're tiny one-dimensional loops of energy strings, vibrating in patterns that determine what we perceive as mass charge and force. And at the Planck scale, where these strings vibrate, space-time doesn't just become discrete. It becomes wildly, violently unstable, a churning foam of quantum fluctuations so extreme that the very geometry of space and time loses meaning. The story of string theory begins in 1968, though no one realized it at the time. A young physicist named Gabriele Veneziano was trying to understand the strong nuclear force, the force that holds quarks together inside protons and neutrons. The equations were impossibly complicated, but Veneziano stumbled upon an old mathematical function, the Euler beta function discovered in the 18th century, and found that it described the behavior of strongly interacting particles almost perfectly. It was a strange discovery. Why would an obscure function from pure mathematics describe particle physics? In 1970, three physicists, Yoichiro Nambu, Holger, Bech, Nielsen, and Leonard Susskind, independently realized what Veneziano's equation was actually describing, not point particles but tiny vibrating strings. Imagine replacing every particle in the universe with a tiny loop of energy, like a rubber band vibrating at different frequencies. A string vibrating one way looks like an electron. Vibrating another way, it looks like a quark. Another frequency, and it's a photon. All particles in this picture are just different vibrational modes of the same fundamental object. It was an elegant idea, but almost immediately it ran into problems. The equations only worked if the strings existed in 26 dimensions, far more than the 4 we experience, 3 of space, 1 of time. And worse, the theory predicted a particle that didn't seem to exist, a massless particle with spin 2 traveling at the speed of light. For years, string theory was considered a failure. Most physicists abandoned it. It seemed like a beautiful mathematical curiosity that had nothing to do with reality. But in 1974, two physicists, John Schwartz and Joel Shirk, realized something extraordinary. That mysterious massless spin 2 particle. It wasn't a bug, it was a graviton, the hypothetical quantum particle that carries the gravitational force. String theory wasn't just a theory of particles, it was a theory of quantum gravity. Suddenly, everything changed. By the 1980s, string theory had been refined. Physicists discovered that the equations work better in 10 dimensions rather than 26, and they developed 5 different versions of the theory, each describing the universe in slightly different ways. In 1995, Edward Witten showed that all 5 versions were connected different perspectives on a single deeper theory he called M theory, which exists in 11 dimensions. But here's the question. Everyone asks, if the universe has 10 or 11 dimensions, where are the extra ones? The answer is that they are curled up, compactified into shapes so small we can't see them. Imagine an ant walking on a tightrope. To the ant, the rope is a one-dimensional line. But zoom in close enough, and you'd see the rope has thickness. It's actually a cylinder with a second dimension curled into a tiny circle. From far away, that second dimension is invisible. String theorists suggest the extra dimensions work the same way. They exist, but they're curled up into incredibly tiny shapes with sizes, on the order of the Planck length 1035 meters. These shapes are called Calabi-Yau manifolds, named after mathematicians Eugenio Calabi and Xing-Tung Yau. They're stunningly complex 6-dimensional geometries, and the way they're shaped determines the properties of particles in our universe. Their masses charges how they interact. In other words, the hidden dimensions give space-time its texture. But here's where it connects to our question about smoothness. In string theory, space-time at large scales, at human scales, planetary scales, even atomic scales look smooth and continuous, just as general relativity predicts. But zoom down to the Planck scale and things get strange. At the Planck scale, strings are about 1035 meters long, roughly the Planck length. They're vibrating, oscillating, moving through the curved geometry of space-time. But space-time itself, at this scale, is not stable. Here's why. In quantum mechanics, the vacuum is never truly empty. It's filled with quantum fluctuations, virtual particles popping in and out of existence, borrowing energy from the void and paying it back almost instantly. These fluctuations are tiny at large scales, but at the Planck scale, they become enormous, and in general relativity energy curve space-time. So, if the vacuum is fluctuating with enormous amounts of energy at the Planck scale, space-time itself should be fluctuating wildly. In 1978, Stephen Hawking explored what this means. He called it quantum foam, the same term John Wheeler had coined 2 decades earlier. But Hawking went further. He calculated what the foam would look like. At the Planck scale, Hawking suggested space-time is a seething chaos of quantum fluctuations. Virtual black holes flicker into existence and evaporate in 10^43 seconds. Wormholes open and close. The topology of space itself, whether it's connected or disconnected, smooth or torn, becomes uncertain, probabilistic. It's as if space-time is boiling. Imagine looking at the surface of water. From a distance, it looks smooth, but get close enough molecular scale, and you see individual water molecules jostling, vibrating, colliding. The smoothness was an illusion created by averaging over countless tiny fluctuations. Hawking suggested space-time works the same way. At large scales, the quantum foam averages out into the smooth, predictable geometry of general relativity. But at the Planck scale, geometry itself becomes probabilistic. Distances flicker, angles shift. The concept of here and there loses meaning. In string theory, this foam is even more complex because the strings themselves are moving through it. A string isn't just a passive thread floating in space, it's an active participant in the geometry. The way a string vibrates depends on the curvature of space-time around it, and the energy of the string curves space-time in turn. At the Planck scale, this feedback loop becomes extreme. Strings vibrate, creating energy. Energy curves space-time. Curved space-time changes how strings vibrate. And the cycle repeats faster than anything can stabilize it. The result is quantum chaos. But here's the fascinating part. String theory suggests that space-time might not be fundamental at all. In recent decades, some string theorists have proposed that space-time emerges from something deeper, from quantum entanglement, from information from relationships between strings. Space-time in this view is not the stage on which physics happens. It's a phenomenon that arises when you zoom out, when you average over the quantum details, when the foam settles into something that looks smooth and geometrical. This idea that space-time is emergent, not fundamental, has become one of the hottest topics in theoretical physics. It's been explored through the holographic principle, through quantum entanglement, through the AD-SU-CFT correspondence, a mathematical duality discovered by Juan Maldacena in 1997 that shows space-time in one universe can be equivalent to quantum mechanics in a lower dimensional universe without gravity. It's a vision that would have been unimaginable a century ago. Space and time, the most basic aspects of reality, might be illusions, convenient approximations that emerge only at scales where quantum effects average out. But does string theory work? Can it describe the real universe? The honest answer is we don't know yet. String theory has been extraordinarily successful mathematically. It unifies quantum mechanics and general relativity into a single consistent framework, something no other theory has achieved. It predicts gravitons. It explains black hole entropy. It has led to profound insights in pure mathematics solving problems that mathematicians had been stuck on for decades. But it has one glaring weakness. It doesn't make testable predictions. Or rather, it makes too many predictions. Depending on how you curl up the extra dimensions, you get different universes with different laws of physics. There might be 10 to 500 possible Calabi-Yau shapes, each one corresponding to a different universe. This is called the string theory landscape, and it's been a source of deep frustration. If string theory can describe almost any universe, how do we know it describes our universe? Some physicists argue that this is actually a feature, not a bug. Maybe all those universes exist a vast multiverse with every possible combination of physical laws realized somewhere. We happen to live in one where the laws allow for stars, planets, and life. Elsewhere, the laws are different. It's called the anthropic principle, and it's deeply controversial. Some see it as a profound insight into the nature of reality. Others see it as giving up on the search for a unique predictive theory. And yet, string theory persists. Thousands of physicists around the world continue working on it, refining the mathematics, searching for connections to observable phenomena. One hope is that string theory might leave subtle traces in gravitational waves, ripples in space-time created by colliding black holes or neutron stars. If space-time has extra dimensions or quantum foam at the Planck scale, gravitational waves might travel slightly differently than general relativity predicts. Future detectors more sensitive than LIGO might be able to see these differences. Another hope is cosmology. If the universe underwent a period of rapid expansion called inflation, something most cosmologists believe happened, then quantum fluctuations during inflation might have been influenced by stringy effects. These fluctuations would leave patterns in the cosmic microwave, background patterns we might be able to detect. So far, no one has found definitive evidence. But the search continues. And here's the thing that's easy to forget. String theory and loop quantum gravity are not enemies. They're two different paths up the same mountain, two attempts to answer the same fundamental question. What happens to space-time at the Planck scale? Loop quantum gravity says space-time is woven from discrete quantum threads. String theory says space-time is a foam of quantum fluctuations stabilized by vibrating strings. Both agree on one thing: smoothness at the smallest scales is an illusion. At the Planck scale, the universe is not a smooth stage. It's a wild, fluctuating, uncertain place where geometry itself becomes probabilistic, where distance and time lose their familiar meanings, where the fabric of reality trembles at the edge of chaos. And yet, somehow, when you zoom out, when you average over all those fluctuations, all that quantum chaos, it settles into the smooth, predictable space-time we experience every day. It's as if the universe knows how to hide its strangeness, as if it smooths itself out just enough, just far enough from the Planck scale so that we can walk through rooms, measure distances, trust that space and time are continuous. But beneath that surface, the foam is still there, seething, vibrating, waiting. Imagine standing at the edge of the ocean at midnight. The water is black and visible. You can't see the waves, can't measure their height or shape. But every so often a wave crashes against the shore, and in that brief moment, in the sound and the spray, in the way the sand shifts beneath your feet, you learn something about what's out there in the dark. This is how we search for quantum gravity. We can't see the Planck scale. We can't build microscopes powerful enough to zoom in on the texture of space-time. The energy required is impossibly large. The distance is impossibly small. Direct observation might be forever beyond our reach. But the universe is vast, and light has been traveling through space for billions of years, crossing distances so enormous that even the tiniest effects we could never measure in a laboratory might accumulate into something detectable. So scientists have begun looking for echoes, faint traces, subtle hints that space-time at its smallest scales is not perfectly smooth. They're searching in the light from the most distant explosions in the universe, in the ripples of gravitational waves crossing the cosmos, in the paths of particles traveling at nearly the speed of light. And every so often, they find something strange. The first place to look is in light itself, specifically in gamma-ray bursts. Gamma-ray bursts are among the most violent events in the universe. They occur when massive stars collapse into black holes, or when neutron stars collide, releasing in a few seconds more energy than the sun will produce in its entire 10 billion-year lifetime. The light from these explosions travels across billions of light years before reaching Earth. And here's the key. If space-time is grainy at the Planck scale, light traveling through it might be affected. Think of it this way. Imagine you're driving on a road. If the road is perfectly smooth, your car glides along effortlessly, and all four wheels experience the same surface. But if the road is slightly rough, paved with tiny pebbles, the wheels experience tiny bumps. Each bump is negligible on its own, but over a long journey, those tiny bumps accumulate. Your car vibrates. The ride feels different. Light traveling through quantum space-time might experience something similar. If space has a discrete structure at the Planck scale, photons might interact with that structure just barely, just slightly, in a way that depends on their energy. High-energy photons, gamma rays, have shorter wavelengths. They see smaller structures. Low-energy photons, visible light radio waves, have longer wavelengths and are less sensitive to tiny graininess. So, if space-time is grainy, high-energy photons might travel at slightly different speeds than low-energy photons. The difference would be infinitesimally small, perhaps 1 part in 1035. But if those photons travel for billions of years, the tiny difference might accumulate into something measurable, a delay. In 1998, physicists Giovanni Amelino, Camelia, John Ellis, and others suggested searching for this effect in gamma-ray bursts. If a burst emits both high-energy and low-energy photons at the same instant, and those photons travel for billions of light years, they might arrive at Earth at slightly different times, with the high-energy photons arriving a fraction of a second earlier or later, depending on the details of quantum space-time. It was a brilliant idea, but extraordinarily difficult to test. The problem is that gamma-ray bursts are chaotic events. They don't emit all their photons at once, they flicker flare pulse over seconds or minutes. So, even if high-energy and low-energy photons arrive at different times, you can't be sure whether that's because of quantum gravity or simply because they were emitted at different moments. You need a burst that's extremely bright, extremely distant, and emits photons across a wide range of energies in a very short time. And you need telescopes sensitive enough to detect the arrival time of individual photons with millisecond precision. By the 2000s, we had those telescopes. NASA's Fermi Gamma Ray Space Telescope, launched in 2008, was designed to study gamma ray bursts with unprecedented precision. It could detect photons with energies ranging from a few thousand electron volts up to 300 billion electron volts, a factor of millions. And on May 10th, 2009, Fermi detected something remarkable, GRB 090510. A gamma ray burst from a galaxy 7.3 billion light-years away. The burst was incredibly bright and incredibly brief. Most of its energy was released in less than a second. Fermi detected thousands of photons ranging from low-energy gamma rays to photons with energies above 30 billion electron volts, some of the highest energy photons ever observed from a gamma ray burst. And here's what was remarkable: despite traveling for 3 billion years, more than half the current age of the universe, the high energy and low energy photons arrive within milliseconds of each other. This was a problem for some quantum gravity theories. If space-time has the kind of grainy structure predicted by certain models, high-energy photons traveling 7.3 billion light-years should have arrived seconds, maybe even minutes after low-energy photons, but they didn't. They arrived almost simultaneously. The Fermi team calculated that this observation ruled out certain versions of quantum space-time, specifically models, where the speed of light depends strongly on photon energy. The Planck scale structure, if it exists, must be more subtle than those models predicted. But the story didn't end there. In 2019, astronomers observed another gamma-ray burst, GRB 1901's 14C, at a distance of about 4.5 billion light-years. This burst was detected by multiple telescopes, including the MAGIC telescope array in the Canary Islands, which observed extremely high-energy gamma rays arriving from the burst. Some researchers analyzing this data claim they found a tiny delay, a hint that high-energy photons had traveled slightly slower than expected. The delay was small, just barely at the edge of detectability, and other teams disputed the finding. The debate continues. Some observations show hints of energy-dependent delays. Others show no delays at all. The data is frustratingly inconclusive. But here's the lesson: we're now at the edge of being able to test quantum gravity. A century ago, the Planck scale seemed forever beyond reach. Today we're analyzing light that's traveled billions of years, searching for effects that accumulate over cosmic distances. The Planck scale is still invisible, but its shadow perhaps is beginning to show. Another place to search is in gravitational waves, ripples in space-time itself, caused by colliding black holes or neutron stars. On September 14, 2015, the LIGO detectors in Louisiana and Washington State detected the first gravitational wave ever observed, a signal from two black holes, each about 30 times the mass of the Sun, that merged together 1.3 billion light-years away. It was one of the most important discoveries in the history of physics. But it also opened a new way to search for quantum gravity. Gravitational waves travel at the speed of light, carrying information about the collisions that created them. And just like light, gravitational waves might be affected by the quantum structure of space-time. If space-time is grainy at the Planck scale, gravitational waves passing through, it might experience a kind of friction, a tiny drag that depends on their frequency. High-frequency ripples might travel slightly slower than low-frequency ones. Over billions of light-years, this tiny difference might accumulate into a measurable effect called dispersion. LIGO scientists have searched for dispersion in the gravitational waves they've detected. So far, they've found none. The waves arrive exactly as general relativity predicts, with no evidence of quantum space-time effects. But LIGO's sensitivity is limited. The gravitational waves it detects come from relatively nearby sources, at most a few billion light-years away. To see quantum gravity effects, we might need to detect waves from much farther away or with much greater precision. Future detectors might provide that precision. LISA. The Laser Interferometer Space Antenna is a planned space-based gravitational wave observatory that will be far more sensitive than LIGO. It will detect waves from supermassive black hole mergers billions of light years away, waves that have traveled through space-time for most of the universe's history. If quantum space-time exists, Lisa might finally see it. A third place to search is in cosmic rays high-energy particles from space that constantly bombard Earth's atmosphere. Some cosmic rays carry truly staggering amounts of energy. In 1991, a detector in Utah recorded a cosmic ray with an energy of about 3x 10 to the 20 electron volts, roughly the energy of a baseball thrown at 60 miles per hour, concentrated into a single subatomic particle. These ultra-high energy cosmic rays are incredibly rare. Only a few strike Earth per square kilometer per century. And they're deeply mysterious. We don't know where they come from or how they're accelerated to such extreme energies. But here's the interesting part. At such high energies, particles might begin to feel the quantum structure of space-time. In normal space-time, there's a fundamental limit to how much energy a particle can have while still being able to travel long distances. It's called the GZK cutoff, named after physicists Kenneth Greisen, Vadim Kuzmin, and Georgy Zatsepin, who calculated it in 1966. The limit exists because ultra-high energy protons collide with photons in the cosmic microwave background, the faint afterglow of the Big Bang, and lose energy through particle creation. Above about 5x 10^19 electron volts, protons traveling more than about 50 million light years should lose so much energy that they can't reach Earth. And yet, we've detected cosmic rays above that energy. A few, rare ones. But they exist. Some physicists have suggested that quantum spacetime might modify the GZK cutoff. If space-time is grainy at the Planck scale, the effective speed of light might be slightly different for ultra-high energy particles, or the interactions with background photons might be slightly weaker. This could allow particles to travel farther than expected. It's a speculative idea, and the data is sparse. But it's another place where quantum gravity might leave traces subtle violations of predictions based on smooth space-time. The challenge in all of these searches is the same: quantum gravity effects are extraordinarily weak. The Planck scale is 10^35 meters. The scales we can directly probe using particle accelerators, using telescopes, using gravitational wave detectors are at best 10^19 meters. That's a gap of 16 orders of magnitude, a quadrillion times smaller. To see quantum gravity effects, we need signals that have traveled enormous distances, billions of light years, so that tiny Planck-scale effects can accumulate into something detectable. But over such distances, other effects, astrophysical effects, measurement, uncertainties, random noise can easily overwhelm the tiny signal we're searching for. It's like trying to hear a whisper in a thunderstorm, and yet the search continues, because the stakes are so high. If we could detect even a single unambiguous signature of quantum spacetime, a delay in gamma rays dispersion, in gravitational waves, a violation of the GZK cutoff, it would be one of the greatest discoveries in the history of science. It would tell us that space and time are not fundamental, that smoothness is an illusion, that the fabric of reality has a texture we've never seen. It would confirm that at the smallest scales, the universe is discrete, granular, quantum, and it would open entirely new questions. What are those grains made of? How do they connect? How does smooth space-time emerge from them? Does time really tick, or is that just another approximation? For now, the evidence is inconclusive. Some observations hint at something strange. Others show nothing at all. The data dances at the edge of detectability, frustrating and tantalizing in equal measure. But here's the beautiful part: we're looking. We're asking. We're not content to say the Planck scale is forever beyond reach. We're searching the oldest light, listening to the deepest vibrations, analyzing the highest energy particles, hoping to catch a glimpse, just one glimpse of the texture beneath everything. And if space-time really is grainy, if smoothness really is an illusion, Then somewhere out there in the cosmos, hidden in signals we haven't yet decoded, the proof is waiting. If space-time is not smooth, if it really does crumble into discrete quantum threads or foam at the Planck scale, then everything we think we understand about reality shifts, not just in abstract theoretical ways, but in profound fundamental ways that touch the deepest questions we've ever asked. Questions about beginnings and endings, about cause and effect, about whether the universe had to exist at all, or whether it simply does. Because smoothness isn't just a mathematical convenience. It's been the foundation of how we understand motion time, causality, the very flow of existence itself. And if that foundation dissolves at the smallest scales, then the universe we thought we knew might be something entirely different. Let's start with the most immediate consequence, what happens between moments. In our everyday experience, time flows. 1 second follows another smoothly, continuously. You can always imagine dividing time into smaller pieces, milliseconds, microseconds, nanoseconds, going smaller and smaller without end. But if time is quantized, if it comes in discrete Planck time ticks of 5.4 × 10^44 seconds, then something strange happens. Between one tick and the next, there is no time. Not a very short time. Not an infinitesimally small time, no time at all. It's like watching a movie. Each frame is a frozen image. The next frame is also frozen. The motion you see, the illusion of continuity, exists only because your brain stitches the frames together. But between the frames, there is nothing. No motion, no change, just a gap. If time really works this way, then the universe doesn't flow. It ticks. And in the gaps between ticks, causality, the idea that every effect has a cause, becomes strange. Imagine an electron moving through space. In smooth time, it traces a continuous path, moving from one location to another, through every intermediate point. Cause and effect are clear. The electron was here, so now it's there. And the reason is that it traveled. But in quantized time, the electron exists at one location in one tick and a different location in the next tick. There is no traveling between. There's no continuous path. The electron simply is here, then is there. Does that break causality? Or does it mean causality itself is an emergent phenomenon, something that only appears when you zoom out and average over many ticks? Physicists don't know. The question is still open. Some researchers believe causality remains intact, even in quantized time, because the quantum state of the universe evolves according to rules, the Schrödinger equation, or its relativistic cousins, that preserve the connection between past and future. The ticks might be discrete, but the evolution is still deterministic. Others suggest that causality at the Planck scale might be probabilistic rather than deterministic. The universe doesn't follow a single path from one tick to the next. It explores many possible paths. And what we perceive as causality is just the most probable sequence. It's a question that touches philosophy as much as physics. And it matters because causality is how we make sense of the world. If it breaks down at the Planck scale, then the universe at its deepest level is not a chain of causes and effects. It's something stranger, a web of probabilities, a network of relationships, a dance of quantum states that only looks causal when you step back far enough. Now consider an even deeper question. What happened at the beginning of the universe? In standard cosmology, if you trace the universe backward in time, it gets smaller and smaller, denser and hotter. About 13.8 billion years ago, you reach a moment called the Big Bang. A singularity where density becomes infinite, temperature becomes infinite, and the equations of general relativity break down completely. Physicists have always been uncomfortable with this. Singularities are places where physics stops working, where the math returns nonsense. They're a sign that the theory is incomplete. But if space-time is quantized, the singularity disappears. Here's why. In general relativity, there's no limit to how small the universe can get. You can compress it to a 0.0 volume infinite density. But in quantum spacetime, there is a limit the Planck volume about 4x 10 105 cubic meters. You can't compress space beyond that. There is no smaller. The Planck volume is the smallest possible volume, the quantum of space itself. So if you trace the universe backward in time in a quantum theory of gravity, it doesn't collapse to a singularity. Instead, it compresses down to a region of Planck scale size, unimaginably tiny, yes, but not zero, not infinite. And then something remarkable happens. At the Planck scale, quantum effects become dominant. The uncertainty principle kicks in with full force. And some theories, particularly loop quantum cosmology, a version of loop quantum gravity applied to the entire universe, predict that quantum effects create a kind of repulsive force at these extreme densities. The universe compresses, reaches the Planck scale, and then bounces. This is called the Big Bounce. In 2001, physicist Martin Bojewald used loop quantum cosmology to model the very early universe. He found that instead of a singularity, the universe undergoes a smooth transition, a bounce where contraction turns into expansion. The Big Bang in this picture wasn't the beginning of time. It was a transition, a moment when a previous collapsing universe reached its quantum limit and rebounded into the expanding universe we see today. This idea is profound. It means the universe might not have a beginning at all. Time might extend infinitely into the past, with the universe cycling through contractions and expansions, each bounce occurring at the Planck scale. It solves the problem of the singularity. It eliminates the need to ask what came before the Big Bang, because there was before a previous phase of the universe compressed, but not destroyed. Of course, this is speculative. We don't have direct evidence of a bounce, but it's a prediction that emerges naturally from quantum spacetime, and it transforms one of the deepest mysteries in cosmology into a testable hypothesis. Some researchers have even suggested that traces of the bounce might be visible in the cosmic microwave background, the faint afterglow of the Big Bang. If the universe bounced, quantum fluctuations from the contracting phase might have carried over into the expanding phase, leaving subtle patterns in the CMB that we could in principle detect. So far, no such patterns have been found. But the search continues. Black holes, too, are transformed by quantum spacetime. In general relativity, if you fall into a black hole, you eventually reach the singularity at the center, a point where space-time curvature becomes infinite, where tidal forces become infinite, where everything is crushed to zero volume. It's a place where physics ends, where the equations break, where even time ceases to have meaning. But if space-time is quantized, that singularity vanishes, just as the Big Bang singularity is replaced by a Planck scale bounce. The black hole singularity is replaced by a Planck scale core, a region of extreme but not infinite density and curvature. Loop quantum gravity researchers have modeled this. They find that at the center of a black hole, where general relativity predicts infinite density quantum effects take over, space becomes a dense tangle of quantum geometry, spin networks twisted into complex fluctuating patterns. But it's finite, bounded, comprehensible, at least in principle. This has profound implications for one of the biggest unsolved problems in theoretical physics, the black hole information paradox. In the 1970s, Stephen Hawking discovered that black holes aren't entirely black. Due to quantum effects near the event horizon, they emit radiation now called Hawking radiation, and over immense timescales they evaporate completely. But here's the problem. If information falls into a black hole and the black hole evaporates, where does the information go? In quantum mechanics, information can't be destroyed. It must be preserved somehow. But if it's lost in a singularity, it seems to vanish. This is the information paradox. Quantum spacetime might solve it. If there's no singularity, only a Planck-scale quantum core, then information isn't destroyed. It's encoded in the quantum structure of the core itself. As the black hole evaporates, the information is gradually released back into the universe through the Hawking radiation. Exactly how this happens is still unclear, but the key point is this: by eliminating the singularity, quantum space-time opens the door to preserving information, to reconciling general relativity with quantum mechanics, to resolving one of the deepest contradictions in modern physics. But there's something even more unsettling to consider. If time is discrete, if it really does advance in ticks rather than flowing smoothly, then what we experience as now might not be fundamental. It might be an illusion, a way our brains interpret the sequence of quantum states. Carlo Rovelli, one of the founders of loop quantum gravity, has written extensively about this. He argues that time as we experience it doesn't exist at the fundamental level. There is no universal now that extends across the universe. There's only change, one quantum state transitioning to another. And we embedded in that sequence perceive those transitions as the flow of time. It's a radical idea, and if it's true, it means the past and future are not fundamentally different from space. They're just directions in a four-dimensional structure, or perhaps a quantum network that we move through, or that moves through us. In this view, the question, what time is it, has no absolute answer. Time is relational, defined only by the configuration of the quantum network at any given point. There is no clock ticking at the heart of the universe. There are only changes, relationships, transitions. And now, this moment, this experience of being present, is simply the way our minds organize the flow of quantum information arriving from the network around us. It's a beautiful, disorienting thought. And it raises yet another question. What about free will? If time is discrete, if the universe advances in Planck time ticks, does that mean the future is already determined? Or does the probabilistic nature of quantum mechanics leave room for genuine unpredictability? The answer depends on how you interpret quantum mechanics. In some interpretations, the universe follows a single deterministic path through the quantum network, and the appearance of randomness is just our ignorance of the full state. In others, the universe genuinely branches, splitting into multiple paths at every quantum transition, and free will is the experience of navigating through one of those branches. No one knows which interpretation is correct. And perhaps no one ever will, because the question touches the boundary between physics and philosophy, a boundary that becomes impossibly blurry at the Planck scale. But here's what we can say with confidence. If space-time is quantized, then the universe at its most fundamental level is not the smooth, continuous, deterministic clockwork that Newton imagined, or even the smooth curved fabric that Einstein described. It's a network, a web, a structure built from discrete quantum threads evolving in discrete quantum steps, with smoothness and continuity emerging only when you zoom out, when you average over the chaos, when you step back far enough that the pixels blur into an image. And our thoughts, our memories, our sense of self, are patterns in that network. We are not separate from space-time. We are woven into it, made of it, inseparable from the quantum geometry that stitches reality together. It's a vision that's humbling and awe-inspiring in equal measure, because it means that asking, what is space-time made of, is not just a question about physics. It's a question about us, about what we are, where we came from, how we fit into the fabric of existence. And the answer, if we ever find it, will change not just our understanding of the universe, but our understanding of ourselves. But all of this is still theory, still speculation, still mathematics whispered at the edge of what's knowable. So, let's return to where we began, to the simple question that started this journey. We began with a simple question, whispered in the dark. What if the universe isn't smooth? We've walked a long path since then, through centuries of assumption where space and time seemed infinite and continuous, through the shock of quantum mechanics when we discovered that energy and matter come in discrete packets, through the mathematics of the Planck scale, where distance and time themselves dissolve into uncertainty. We've explored two grand visions, loop quantum gravity, which weaves space from quantum threads and string theory, which sees reality as vibrations in a foam of fluctuating dimensions. We've searched for evidence in the oldest light from gamma-ray bursts in the ripples of gravitational waves in particles carrying impossible energies across cosmic distances. And we've asked what it would truly mean if space-time crumbles at its foundation. What it would mean for the Big Bang, for black holes, for causality itself. For the flow of time, we trust the continuity we take for granted, the smoothness we have never questioned until now. So, where does that leave us? The honest answer is we don't know yet. We don't know if space-time is really quantized. We don't know if it's woven from loops or vibrating strings or something else entirely. Something we haven't imagined yet, something that doesn't fit into any theory we've built. We don't know if the Planck scale is a boundary we'll ever cross, even indirectly. We don't know if the foam is real or just a mathematical shadow. A placeholder for physics we haven't discovered. All we have are equations that whisper experiments, that hint observations, that tease at the edge of detectability. But here's what we do know. We know that every time humanity has looked closer, we've found that reality is stranger than we imagined. We thought matter was continuous. It's made of atoms. We thought atoms were fundamental. They're made of electrons and nuclei. We thought nuclei were indivisible. They're made of protons and neutrons. We thought protons were elementary. They're made of quarks. Every layer we've peeled back has revealed something more fundamental, more beautiful, more unexpected. And there's no reason to think we've reached the bottom yet. The Planck scale might be the final layer, the place where questions stop making sense, where the concept of smaller ceases to have meaning. Or it might be just another threshold beyond which lies something even stranger, even deeper. We won't know until we look. And we are looking. Right now, telescopes are scanning the sky for gamma-ray bursts, searching for that telltale delay that would prove space has texture. Gravitational wave detectors are listening for dispersion in the fabric of space-time. Particle physicists are analyzing cosmic rays looking for violations of the rules we thought were absolute. And theorists, thousands of them around the world, are refining the mathematics, searching for new ways to test quantum gravity, new predictions that might finally bridge the gap between theory and observation. It's slow work, frustrating work. The universe guards its deepest secrets carefully. But every so often there's a breakthrough, a new observation, a new calculation, a new way of thinking about the problem. And the picture becomes a little clearer. Maybe in our lifetimes we'll know. Maybe a detector will find that faint signal, that whisper from the Planck scale, and confirm that space-time really is discrete. Or maybe we'll find nothing and realize that smoothness goes deeper than we thought, that continuity is more fundamental than quantum mechanics suggested. Either way, we'll learn something profound about the nature of reality. But let's step back for a moment. Let's remember why this question matters. It's not just about abstract mathematics or untestable theories. It's about understanding the fabric of existence itself, the stage on which everything happens, the grid that gives structure to space and time, the foundation beneath every atom, every thought, every moment. If space-time is smooth, then the universe is continuous infinite in its divisibility, flowing like water from past to future. It's the universe Newton imagined, refined and curved by Einstein, but still fundamentally the same, a stage that exists independently of the actors on it. But if space-time is quantized, then the universe is fundamentally different. It's discrete, woven, relational. Space and time are not containers, but connections. The stage doesn't exist separately. It's made of the same quantum threads as everything else. There is no background, no void, no emptiness beneath. Just the network itself, connecting, evolving, creating the illusion of smoothness through its collective structure. And we, our bodies, our thoughts, our consciousness, are patterns in that network. Not separate from space-time, but woven into it, made of it. Inseparable from the quantum geometry that stitches everything together. It's a vision that blurs the boundary between physics and philosophy, between science and something deeper, something almost spiritual in its implications. Because if we're truly part of the network, if there's no separation between us and the fabric of reality, then in some sense the universe is experiencing itself through us. Our questions about space-time are space-time questioning its own nature. It's a thought that feels too large to hold. But maybe that's the point. Maybe the deepest questions don't have answers that fit neatly into equations. Maybe they have answers that change how we see ourselves, how we understand our place in the cosmos, how we relate to the vast, mysterious, beautiful structure we call reality. Think about it this way. A century ago, we thought the universe was static, eternal, unchanging. Then Edwin Hubble discovered it was expanding, and suddenly we realized the cosmos has a history, a beginning, a story, an evolution. 50 years ago, we thought space was mostly empty. Then we discovered dark matter and dark energy and realized that everything we can see, stars, galaxies, planets, us makes up only about 5% of the universe. The rest is invisible, mysterious, unknown. And now we're asking whether space and time themselves, the most basic aspects of reality, are smooth or discrete, continuous or quantized, fundamental or emergent. Each question peels back another layer. Each answer reveals something we didn't expect. And the pattern suggests that we'll never reach a final answer, a ultimate theory, a place where we can stop and say, now we understand everything, because the universe is deeper than that. Stranger than that, more layered, more subtle, more endlessly surprising than any theory we build. And maybe that's the most beautiful thing about science, not that it gives us final answers, but that it keeps opening new questions, deeper mysteries, further horizons. The Planck scale is one of those horizons. It's a boundary we might never cross directly. But it's also an invitation to imagine, to calculate, to observe, to wonder what lies beyond the edge of the knowable. And in that wondering, we become part of the story, part of the universe's long, slow process of understanding itself. So, what if space-time isn't smooth? What if beneath the surface we trust, there's a foam, a network, a weaving of quantum threads thinner than thought? What if the fabric of reality is pixelated, and we're just too large, too slow, too distant to see the grain? It wouldn't change how you move through the world. You'd still walk across rooms, cross distances, experience the flow of time from moment to moment. The smoothness you perceive would still be real, just emergent approximate a pattern that appears when you zoom out. But it would change what that movement means. It would change what space and time are at their core. It would change the story we tell about the universe and our place in it. And maybe that's enough. Maybe the question itself, the search, the wondering, the slow accumulation of evidence and theory, is as important as any answer we might find. Because in asking it, we're doing what humans have always done. We're looking at the world around us and refusing to take it at face value. We're digging deeper, questioning, harder imagining possibilities that no one has imagined before. We're trying to see the invisible, to measure the unmeasurable, to know the unknowable. And even if we never fully succeed, even if the Planck scale remains forever beyond direct observation, we'll have learned something profound just by trying. We'll have learned that reality is not what it seems, that beneath the surfaces we trust, there are always deeper layers, that the universe is endlessly more subtle, more strange, more wonderful than we could have guessed. And we'll have learned that we belong to that strangeness, that we're not observers standing outside reality looking in. We're part of it, woven into it, made of the same quantum threads, the same fluctuating foam, the same mysterious, beautiful, incomprehensible structure. So, tonight as you drift towards sleep, imagine the space around you, the empty air, the distances between things, the seconds ticking forward. Imagine zooming in past atoms, past nuclei, past quarks all the way down to the Planck scale where the fabric might fray, where geometry might foam, where the smoothness might finally end. You won't ever see it, not directly, but knowing it might be there, knowing that beneath everything you trust, there's something stranger, something deeper, something that connects you to every other part of the universe in ways we're only beginning to understand. Knowing that changes something. It makes the world a little more mysterious, a little more magical, a little more worth wondering about. And maybe that's all we need, not final answers, not complete theories. Just the knowledge that the universe is deeper than it looks, and that we're part of that depth, connected, woven, inseparable from the fabric itself. So, rest in that uncertainty. Drift in the not knowing. Let the questions carry you gently into dreams. Space might be smooth, or it might crumble into quantum threads. Time might flow, or it might tick in intervals smaller than thought. The universe might have begun with a bang, or with a bounce from a previous cosmos, collapsing and rebounding. We don't know yet. Won't. And that's okay, because the mystery is part of the beauty. The unknown is part of the wonder. And the search, the slow, patient, endless search for deeper understanding, is part of what makes us human. Thank you for drifting with me through this quiet exploration. For walking with Planck and Einstein, with Ravelli and Hawking, with all the minds who dared to ask whether the fabric of reality might not be fabric at all. If these ideas resonated with you, if they made you think or wonder, or see the world a little differently, I hope you'll return. There are always more questions to explore, more mysteries to unfold, more quiet journeys through the strange and beautiful cosmos we call home. Until then, rest well, dream softly, and know that beneath you, around you, within you, the universe is doing something extraordinary, something we're only just beginning to glimpse. The fabric of everything might be woven from threads too small to see, or it might be smooth all the way down. Either way, it's holding you gently, carrying you forward, moment by quantum moment, through the endless, mysterious now. Sleep well, dream of discontinuous time, rest in the foam. Good night.